So welcome to the coating session. Our first presenter will be Markus Klein. He's the managing director of Surago since 2010, and he holds a master degree in business and engineering from the University in Dresden, focusing on microelectronics and electronic packaging. And his past working experiences include Siemens in Singapore, Wacker Chemie AG, Advanced Mass Technology Center, and Fraunhofer Institute for Non-Destructive Testing in Dresden. Markus' expertise focuses on material testing and layer characterization. Please go ahead.
Thank you for the kind introduction. I'm very happy to be here today. I think it's my fifth GPD. And I'm very much enjoying it every time, and it's an awesome venue here. Today I'm going to present inline metrology for coating, for glass coating processes, and at the end I will also talk a little bit about recycling strategies and applications of eddy current systems in this niche. The outline is pretty long, so I will go a little bit through technology, then applications, and process innovations and recycling strategies. Not every one of you knows Suragos yet, but I see many familiar faces that know us. I'm very happy about it. I'm also here to catch up with those folks. We are, for those who don't know us yet, we are founded 2010, focusing with about 50 people, multi-diverse workforce on one technology, which is eddy current testing technology, and we just celebrated 2 weeks ago our anniversary, 15 years, going from 1 to now close to 50 people. Was a tremendous journey, and we met a lot of people and learned a lot of insights about different technologies and applications, and glass is one of our key topics. And our mission is to support process engineers around the world to achieve a resource-efficient manufacturing, and we also want to enable and support fast innovations across industries. And this is what we do with our sensors and instruments, and we also want to push the limits in eddy current sensing. What we do with eddy current sensing is emissivity testing, sheet resistance testing, metal layer thickness testing, glass thickness testing, scribing, checking scribing integrity, and also line resistance for printed electronics. It's applied in layer deposition, layer modification, but also layer removal processes. So everywhere where you add, change, or remove conductive materials. Technology itself is quite industrial application since the 1960s for crack testing. It's basically relying on creating electromagnetic fields which interact with conductive materials. It's a very fast technology. It's non-contact. It can be penetrate through oxide layers. Can be applied in vacuum or in wet or dry environments, and it has a very high repeatability. There are different concepts, measuring from the top, measuring from the bottom, measuring in transmission mode. So that has all different pros and cons. And the key for the architecture glass industry, it correlates with the silver thickness. So the sheet resistance correlates with the silver thickness. So that is basically one aspect. And the other aspect is that the sheet resistance correlates with the emissivity. So emissivity is also one core aspect that we take care of. Another testing method for this sheet resistance is the 4-point probe method, which is a contact method, and which gives the same results but has a lot of disadvantages. And with the eddy current testing approach, we can do portable testing, single point testing for the labs. These kind of tools are used in quality assurance labs for glass around the world. We have customers that have close to 20 of those devices that do this manual testing with that. We have mapping solutions, but the core is inline solutions. And in these inline solutions, there's basically two versions. One is to measure on a moving stage on the left, or having many sensors installed across a web. The applications are around the industry very wide. We have automotive glass testing, mirror coatings testing, smart glass as an application, solar glass as an application. And now I would like to carry you through these different fields where I would like to show you what we do. In architectural glass coating, it's basically characterizing the silver deposition. Tempering is another topic in the value chain, and then the final inspection in the building. This can be applied in vacuum or non-vacuum, but let's go to the silver sputtering as a process itself. Here the strategies are measuring directly after the deposition. There are different sputtering technologies when you can modify the sputtering homogeneity across the glass. Then it also makes sense to measure on different positions across the glass and to directly control the deposition process in the vacuum. Yeah, but very often there's also a final inspection mostly together with an optical system to scan the final inspection of the total glass of the coating stack. Another application is edge removal or glass inspection to make sure that all the conductive layers have been removed. That's one application. Another application is to measure before and after the tempering process. In the tempering, there is basically, it's important what kind of glass do you temper. Do you have a single low E? Do you have double low E? Do you have triple low E? And typically, the people running the tempering furnace need to select the right recipe. And in a night shift, there can be mistakes. Yeah. So one approach is to measure what type of emissivity do I have, what is the glass thickness, what is the emissivity, and also we can check whether the coating is on the right side. Tempering the coating on the wrong side is also an issue. So this can be inspected. And we did some study, I think 2 or 4 years ago, I gave a talk about it here at GPD to test across Finland. We've been to different tempering sites and we presented a lot of data. And we can determine what kind of glass this is. Is this from Saint-Gobain or is this from AGC? So we can detect what kind of glass is coming and automatically feeds this through to the tempering furnace. And then allow automated recipe selection, for instance, is one application. The emissivity changes quite a bit from sometimes 30%. Here's some examples from one glass before tempering and after tempering. There's more data. It's a special topic, so I will not go into this too deep, but it's a good application to know the emissivity before the tempering and feed it directly to the furnace. Another part is windshield testing. So that's basically, a lot of windshields are produced each year, and doing quality assurance there is quite tricky. There's a lot of work done in the lab with manual devices, but there are also inspection strategies to put sensors in line. There's mirror coatings, there's thickness and material weight, there are different units, and there's also more functionalization of mirrors. Sometimes we have displays inside, so we not only have metals, but we have also ITO inside, and there is a variation of topics that are also tested with eddy current inspection. Another topic is antennas in windshields. There's a lot of antennas these days. And of course, there needs to be the formulation of the paste. So we have a sensor which is analyzing the paste when it goes through a pipe and it interacts with electromagnetic fields. So we can see the paste composition, the dielectric and electric properties of this paste, and we can predict processability downstream. Which is one part, and later we can also test the printed antennas and see whether the line resistance is correct or whether there are defects. Very often the optical image does not tell the truth about the electrical performance. Another application is mobile-friendly glass. There is a functionalization possible by also a company which is here. So they are able to add, to make glass which is running in trains, for instance, to make it mobile friendly, that you sit in it and you can see, you can have a good mobile network connection. So this is done by scribing, and we can test the scribing integrity, whether this really works. There are some other aspects that this can be used for. Another application is solar control films as kind of retrofit strategy. And finally, a big application is solar glass. Yeah, solar glass needs to transport the current. So you have a front electrode and backside electrode. Yeah, there are lots of different materials, but it's a nice application. Also important for recycling. Maybe we can come later to that. Eddy current is also able to image electrical performance. So this is kind of not a photo, it's basically a measurement. Each pixel is a measurement, and after a certain time, so roughly 1 minute, 2 minutes, you get such an image depending on the size. And you can see process artifacts or process characteristics and improve homogeneity. Often it's about homogeneity and about finding the right level of sheet resistance. Yeah? Not too much material, not too few, and having the right electrical performance. One more application is smart glass. Smart glass is, I think, 5 years back we had a lot of applications there. Now it's a little bit less. So smart glass also needs to be conductive. So you have a transparent electrode which needs to fulfill optical and also electrical parameters. And there are very many interesting aspects to smart glass deposition. Another application is for display glass. There's a machine in Dresden which is standing at the FEP, which is an ultra thin glass deposition machine, which is good for OLEDs, for instance, because glass has a very good barrier property, and this is also an application. We talked already about automotive mirrors, but there are also other mirrors, of course, and there's also touch panel sensors, which are used to functionalize glass. This is a big trend. Glass is a lot of area. You can do solar, you can do display, you can do touch, you can do all sorts of things, emissivity, and that's so interesting because now things become more and more integrated over time, and of course conductive layers play a big role in activating some of that functions. Of course, I did not touch all the applications. There are heated glass, for instance. There are we have customers that do sensors for like a carpet to see where people walk. There are medical applications, home appliance, and there are many more. And I hope to learn about new applications together with you on this event later today. Now let's talk about sensor innovations. The key for a good sensor is to be able to provide a lot of value. A good value for a sensor is when it's applied very early in the process. So we try to get as close to the deposition as possible. In an optimum world, we would measure during the deposition, but our sensor would block that in some cases, so we go right close to it, as close as possible. But sometimes it's tricky because there are different reasons. Sometimes there's not much space. So we think about how can we have very small sensors or bring the sensors in a way into the machine that they stay mostly outside and they don't take much space in the machine. Another way is to have very small sensors that can be fitted in really tight areas, but at the same time that are able to withstand heat. So we have sensors that can withstand quite some heat, and now we are trying to push the limits up to 500 degrees. At the moment, we are just able to do it up to 220 degrees. So pushing the limits here in this application, these measurements were used to control the tempering. So there was some Ito which was tempered by a certain time. The idea was to get it to 9 ohm per square, and we changed the tempering time and used it for quality control. Another way is to make measurements to, of course, measure in the vacuum, which is basically, let's go to this slide, which is basically kind of a standard application, so you have many sensors in the vacuum. But in some applications, you want to have a traveling sensor, and this is a traveling sensor, so this can go back and forth, and you can have really high resolution across the web or across the glass within the machine. So this is also bringing new capability into the deposition world. These arrays is also interesting. So technically, we can build arrays with 128 sensors, so you have a lot of information. That is also possible in vacuum. And another way is to have sensors. Sometimes we have rotating material like optical lenses or so on. And in this case, it's really nice because it's possible to measure during the deposition. So we can see round by round how the new atoms added to the layer. And then basically you can deposit until you have exactly the number of layers or number of monolayers or the right sheet resistance that you need. The time stopped on my display, so that is kind of risky for me because I tend to talk too long.
We have 5 more minutes, but including the question and answer session.
Okay. So why is this so important? Let's stress the benefits of near process monitoring. Sometimes there are test samples just to just make destructive tests later, so you can avoid that. You can get the feedback within the chamber, do fine-tuning right away, run-to-run control, and improve the deposition, optimize the deposition rate right away. Sometimes you can increase the throughput, but one part is also confidence. Yeah, confidence in what you do, and after you change the target to get back to the level where you want to be. So that was some insights about near process monitoring. Now I would like to bring a new topic to the table, which is basically concepts for recycling. Recycling is something that is not really, many people talk about it, but it's in many industries not thought through fully. I was just at a battery conference. Battery is also a topic where battery recycling, it's more expensive to create a battery that can be dismantled and separated than just plugging it together and shredder it. And similar aspects we have here. So in recycling, there are two routes, in my understanding, to do the recycling during the process. When you deposit on glass and you know, okay, this glass is not good yet, or you collect the trimmings and the edge cuts, and this goes back in the loop, and that works pretty well. For external recycling, I think there can be done more. Solar glass, there's a lot of solar glass upcoming which can be recycled. There's window glass which can be recycled more, and also container glass. There is already quite a good loop. I tried to collect some numbers. So 1.5 million tons generated in the EU alone in construction and demolition, but just a few % of that going to get recycled at the moment, and there's a huge potential. Most of the glass ends up in the landfill, and that's it. Yeah. If you look at the solar glass, we see that there is expected 80 million tons by 2050 globally. And solar glass can be quite good glass, so there's a big potential to recycle that. Of course, there are different types of solar, coated and uncoated glass, but I don't go into this here. And the last part is automotive glass. 27 million vehicles are recycled globally per year. That's a lot of vehicles. And the problem is mostly of this stuff is somehow shredded, and then if it's broken, and it's hard to sort it. Yeah, and that's kind of a challenge. Also, when we look at the windows itself, we have different types of glasses, and if we look at a building which is 50 years old or 40 years old or 20 years old, we don't know exactly what kind of coatings we have.
We have 30 more seconds.
And thank you very much. I work best under pressure. So there are different glasses and there are different potentials. So the idea is that the glass is tested, and there are people here who do it. There's another talk at 4 p.m. I think about that. To measure, go inside of the buildings, test the glass. What type of coating do I have? Is this still a good emissivity, or has it been gone bad? I can plan recycling strategies or refurbishing strategies, and I can also select routes for recycling across that. So that is quite some potential, and I think we will hear more about it in some other GPD. I skip the summary. I'm here right next door and 10 meters away from here, so if you want to hear more about it, just visit me and talk to us. Thanks.